I forgot to do one thing with compression, so we're going to start with compression and talk about compressing over blocks, and then we'll move into the topic of error correction and error detection. So first of all, okay, so we saw already with Huffman that we had a bound on the performance in terms of entropy, right? So the entropy of the information is going to be less than or equal to the expected length for Huffman. We'll use a little subscript h for Huffman of x, which is less than the entropy plus 1 in bits. Okay, so of course all prefix codes have to obey that first inequality, but Huffman being optimal will obey the second one as well. So this here is it's a 1-bit gap in the bounds. Right? We could actually call this the overhead. It's sort of overhead associated with bits being integers in length, right? So we'll see two things. If we encode over blocks, and I'll explain what that means in a minute, but we get two advantages. So the first one is that the overhead becomes negligible. And then the second one is that this can take advantage of correlations, if there are correlations in the sequence of information. Okay, so what we mean by encoding over blocks is something like the following. You have a sequence of information symbols like this. Okay, and instead of what we've talked about so far is each letter would be considered one symbol, and we would then map it to some binary code word in a prefix code. But here what we'll do is we'll say, okay, let's parse this in pairs instead. Okay, and what we can do is we can map each pair of letters. We can have a code that maps pairs of letters to bits. All right, so for the code would be things like, for example, the code would say something like A maps to some big long sequence, and AB maps to some other sequence, and so forth. Okay, and we'd have a code for every pair of letters. It's another way of looking at the problem. So let's look at what I've already listed what we get by doing this. Okay, for one thing, and I want to really emphasize the first one, is that we see that the fundamental limit really is the entropy, that this 1 bit won't matter. We'll see that in a minute. But actually the big benefit will be from number 2. And that is that, notice the text English language is not independent, each letter one after the other, right? If you see a Q, you know very well what's coming next. We know that even though A is a pretty common letter, A followed by A, it may not be that common, whereas A followed by B might be much more common. All right, so these correlations should help us compress further, and if we encode over blocks, it will. All right. So let's do an example without correlation. Just so we can see what item 1 above how that overhead doesn't matter. All right? So let's let, first of all, let's let omega equal these two values, A and B. Those are the letters we're looking at. And let's say probability that x equals A is 0.9. And the probability that x equals B then is 0.1. Okay, so let's first figure out what the entropy of this thing is. So entropy of x should be 0.9 times log base 2 of 1 over 0.9 plus 0.1 times log 2 of 10. Okay, and this is approximately 0.469 bits. So it's less than half a bit of entropy because it's so skewed. A is much more likely than B. All right. Okay, how about the Huffman code? What's the Huffman code for this probability distribution? Yeah, it's just the only good prefix code when you have only two symbols. So A, let's say here's the code. A maps to 0, B maps to 1, or we could switch them so that the lengths will be the same. All right, so you have no choice when you have only two items. So what's the expected length of the Huffman code for this problem? It's 1. Right, the length is 1 all the time. So we're within our bound, right? We knew we would be between entropy and entropy plus 1. But you'd like to somehow take advantage of the fact that you know A's are more likely than B's. All right. So now if we encode over pairs, then what do we have? We have now that we've got pairs x1, x2, which are our values now in omega. Omega now equals AA, AB, BA, BB. Those are possible outcomes. And now we should write out what the probabilities are. Probability of AA equals 0.9 squared, because up here I wrote that we are doing this example without correlation. We're assuming that the letters are independent. Okay? Don't think of actual English. These are independent samples of something. So let's say by independence. Okay, and so that is 0.81. Probability of AB, by symmetry, that's going to equal probability of BA, and that's going to be the product of the two, so 0.09. Okay, and the probability of BB is going to equal 0.01. And these add up to 1, because we have to count the second one twice. Okay, so counting this twice, because I just abbreviated there, but we have two different sequences there. Okay, so let's do the Huffman code then. So what we're going to do is we're going to sort these. I already did them sorted. So we have AA, AB, BA, BB. And their probabilities are 0.81, 0.09, 0.09, 0.01. Okay, and we start constructing by combining the lowest two. Okay, those combine to be 0.1. This is still the largest, 0.81. Still largest, right? And down here we have 0.09. And then on our next step, we combine these two. They stay the smallest, 0.19. Okay, I will use gray to show it, the ones that did not combine. And then finally, like this. Okay, and then we just arbitrarily go assigning labels, 0, 1, 0, 1, 0, 1, and then we shake out our tree to get the code words, or we just write them over here. So C of x1, x2, in this column. AA just gets the code word 0. AB gets the code word 1, 1. BA gets the code word 1, 0, 0. And BB is going to be 1, 0, 1. Okay, so there's a nice prefix code, and you see how it's done what we want it to. It's prioritized short code words for the most likely sequences. But here, now since not everything is taking 2 bits, we should calculate what's the expected length. So the expected length for Huffman here is going to be, we combine these things, we do 0.81 times a length of 1, right, plus 0.09 times 2 plus 0.09 times 3, and then there's the last one times 3, so plus 1 times 3. Okay, when we add this together, we get something around, I'll say approximately equals 1.3 bits. It's the average length. Okay, is this good? Somewhat exciting? Well, it is good because now we've encoded 2 letters at a time. If you want to compare fairly, we should be comparing how many bits we used here divided by the number of symbols that we encoded. All right, so bits per symbol approximately equals 1.3 over 2. Whoops, not over n. Over 2 equals 0.65 bits. Okay, so this is indeed better because now before we had 1, and now we can get down to an average of 0.65 bits. Okay, so we see that we've encoded over blocks. There was no correlation, so we're not taking advantage of the correlation here. We're just taking advantage of shrinking that gap towards entropy. We're still above the entropy. Okay, so let's derive, because remember the entropy was almost a half bit. We're still a little bit above that. Now how could we get closer, do you think, to the entropy? What? Bigger blocks. Do you think if we took the blocks big enough, we'd get arbitrarily close to the entropy? So I saw some yeses and nos. So let's see. Okay. Let's look at bounds for longer blocks. Not for this particular problem, just in general. Okay. So let's let L star sub n be the expected length, be the normalized expected length of the Huffman code for block length n. Okay, so what we mean is what we mean is that L star of n is 1 over n times the expected length of a Huffman code, right, of the sequence x1, x2, ... xn. Okay, so well, what kind of bound can we give it? Well, we know that entropy of x1, x2 up to xn should be a lower bound on n times L star of n. Okay, this is just the bound we've already been looking at, and that should be less than this entropy plus 1. Okay, now the thing is that we talked about what happens to entropy if the random variables in the set are independent of each other. Okay, and the entropy just adds. So this here we're assuming. So this will be n times the entropy of just one of them. Now this is assuming the xi's are independent and they're identically distributed. In other words, we're still using that example where there are no correlations. We're not trying to take advantage of correlations here. So they're just independent samples. They all have the same distribution. Then what we have here is the entropy is n times the entropy of just one of them. All right? And that's going to be true on both sides. So if we divide this by n, we get that the entropy of x is less than or equal to ln star is less than entropy of x plus 1 over n bits. Okay, so this bound where we're squeezing, now the bounds are getting closer as you go to long block lengths, and they do approach entropy. All right. So if you go to long block length, that this overhead part, the second part, is really not an important fundamental part of compression. If you allow yourself to take lengths as long as you want, then entropy is the fundamental limit for lossless compression. All right. Now, in general, we used here very carefully. We used the independence, but English, for example, is not independent from one to the next. So there's something called an entropy rate. And the entropy rate, which is just basically looking at this, how does the entropy of long sequences behave when you divide by n, rather than assuming they're independent. Just if your random process, if this divided by n converges to something, that's the entropy rate. And so the entropy rate is the important thing that, I'll just put that here, which will always be less than or equal to the entropy of just one of them. Right? Entropy rate is so it's just to be aware that that second part of the advantage you get from a block code, if there's correlation, that's going to change the fundamental limit from just the entropy of one symbol to some entropy rate, which is just some vague concept right now to you. But if you're interested, you can learn more about that. Oh, well, what we're really saying is not that even if the block's really big, it's sort of like, just think of a block like 10 or 20 being maybe long enough, okay? Yeah, I mean, the longer, it's still random in that you don't know, I mean, even if the block was as long as a book, you don't know which book it is a priori, right? So if you wanted to compress all possible, PDFs of books, it's still a random process. You can model the distribution of one book being written in another and so forth. Okay, so next, let us do error detection and correction. Now, the first thing we're going to do here, as we started discussing last time, is talk about a specific type of error correction code, the Reed-Solomon code. And this, The reason we're talking about this is not because you need to know the details of Reed-Solomon code. I don't think you'll encounter it in any problem set, not on the final. You don't need to know these fine details of how this code works. But it's just kind of to get the understanding of how codes are applied and what they do in technology. Then we'll look at a specific code, which you can understand much better mathematically. All right, the Hamming code. But first, let's just talk about Reed-Solomon codes. So I have sort of a list of things about Reed-Solomon, so I'm going to try to use the keyboard here. We've already mentioned there are many applications of Reed-Solomon codes. All right. Actually, part of the reason why there are is because these have been around since 1960. All right. So Reed-Solomon codes, they are not the only error correction codes we know, and they're not the best error correction codes we know. They're in terms of efficiency, but they are one of the early discovered good error correcting codes for which you could decode them with reasonable complexity in hardware. So that's one of the reasons why they've been used for so long, and they've been refined over the decades so that you have equipment that can actually encode and decode these things. And like I said before, these are probably the most widely used error correcting codes, and they're in almost everything. But in cases where you really care about the efficiency of the code, you want to get the best performance and not put too much redundancy, because remember, error correction codes are about adding redundancy to help you detect errors. If you really care about that trade-off, you can't get the optimal trade-off with Reed-Solomon codes. You have to go to more advanced codes which have made their way into technology as well, including like cell phones and so forth. Okay, so error correction code, the Reed-Solomon codes actually take blocks of bits, and they treat these as single symbols. Okay, think of it like 10 bits or something. Later, we'll specify exactly what's happening in a CD. All right. Now, they take, let's say, n symbols of information, and then the Reed-Solomon codes add t symbols of redundancy. And these are all parameters. There's many values of n and t that work. All right. And then it can correct errors and erasures. And I should explain what those mean, and then I'll tell you how much they can correct. So errors would be what you think of. You wrote these bits somewhere, you transmitted them over radio frequencies, or you wrote them to a disk, and an error is usually a bit that has been changed. It got read incorrectly at the other end, and you don't even know that the error's there. It's just hiding. The bit has been flipped or something like that, right? Now, an erasure is different. An erasure is if you somehow knew it comes from it's been erased. You somehow know that there is an error at a certain location, all right, but you don't necessarily know how to correct it. Okay. Now, if you knew where errors were in bits, well, if someone told you there's an error here, you'd go flip the bit, right? But remember, the Reed-Solomon codes are acting over groups of bits. So if they have 10 bits, and 1 or 2 of those bits have been changed, according to the Reed-Solomon code, that whole symbol is in error, all right? And therefore, even if you tell it this particular symbol has errors in it, it's not obvious how to correct the errors. Okay, so that would be an erasure. An erasure is an error where the location of the error has been is known. All right. Oh, I did it again. Lost my pen. There it is. Okay, so it can detect as long as the number of 2 times the number of errors plus the number of erasures is less than or equal to t. So t, remember, is the amount of redundant symbols you wrote in. And as long as you have as long as you satisfy this in terms of the number of errors and erasures, then you can correctly, the Reed-Solomon code can correctly decode. So if you think about, say there were no errors, just erasures. And suppose that the erasures were all your redundancy bits, your redundancy symbols. Okay? Well, that's exactly saying all of your redundancy was erased. Of course, you could go fill the redundancy back in, right? I mean, just re-encode it. All right? But what's nice is it does not matter where the erasures happened. So you have this symmetry where it's obvious you could erase all the redundancy bits and get them back, but you can erase any bits you want, I mean, any symbols you want, as long as you don't exceed that number, and you can get them back, right? And then the errors are kind of sort of twice as hard as an erasure. If you have an error in a symbol and you don't know where it is, then you have to have fewer of those to be able to correct. Okay. There's another nice property of these codes here. Okay, if the Reed-Solomon code can't correct, there are too many errors or something, it usually declares failure, and by usually we mean almost always. And this is actually a good thing, because the alternative is that it spits out some other information that's incorrect, and you think it's correct. All right, that could easily happen, right? It fails to in its attempt to correct the information, it corrected to the wrong thing. But that usually doesn't happen in the Reed-Solomon codes, because it's not perfectly efficient in terms of using the redundancy. It means that when you make errors, you're likely, if you introduce too many errors, it's likely that the decoder will just say there's no information that this matches very well. Okay, and let's see. Okay, so now let's talk about the specifics of the Reed-Solomon codes used for CDs. So you have that the symbols are bytes. Okay, so each symbol is 8 bits long. And you have 2 layers, actually, of Reed-Solomon codes used. So we'll talk about these 2 layers because it's actually fun to see. It's a clever reason why they do this. So the encoding is done in the following way. I will use dots to represent bytes to make this picture manageable. You start by taking, in the first layer, you take 24 symbols, which means 24 bytes. So each dot here is one of those bytes. You have 24 of these of the information you're encoding. All right, and you add to it 4 bytes of redundancy using the Reed-Solomon code. All right. Then you go in and you do another row, and I'm going to make it into a grid on purpose here. So you take the next block of 24 bytes of information. Okay. And you, again, encode that. And you do this over a whole bunch of blocks. In fact, you keep doing this until you get to, you've done it 28 times. All right. Then you do what's called interleaving, but in this picture it's very easy to understand. So interleaving is like you shuffle all your bytes around in some known way so you can undo it later. Okay, but the interleaving here is we can understand just by looking down the columns. Okay, so after you've done all of this, you again apply a second layer of Reed-Solomon codes to each column. So now you have 28 bytes here, 28 symbols, to which I add 4 more symbols of redundancy this way. So this means treat this whole column as my new block of information and encode 4 more bytes of redundancy. So this is the second layer after interleaving. Okay, you're doing it over every column, which means, and it may seem kind of funny, that you're going to do it over the redundancy columns as well. So here I'm making redundancy of redundancy, right? I'm feeding that into the Reed-Solomon encoder and getting out new padding, all right? Okay, now finally what you're going to do is to write this onto your medium, and it's a CD, right? To write this actually onto the CD. We're going to read it out column by column and write it in that order on the CD. So this is our 2 layers of Reed-Solomon coding with interleaving, all right? So to recap a little bit, what we did was we wrote. So we write the information by row. Like this. But then I should say read it. A little confusing. Okay, let's say we read it this way. But then write to disk. To disk. I guess it depends on what your view of read and write is. We read the information from its source and enter it in this way. Okay, is what I mean. And then to write it to disk, we go column by column. Okay, now it turns out that this part here is not important. So it actually did not matter at all how we filled in the bytes to the table to begin with, as long as we did it in some way that we can undo, which we can always do, right? So this is not important at all. The writing to disk, it is important that you write it either column by column or row by row. You have to do one of those two to get this to work well, okay? And so just the standard goes column by column. It's not exactly symmetric, right? Because we have 28, columns and 32 rows. So it's not exactly a symmetric thing. For whatever reason, they write it to disk column by column. Okay. Now what's cool about this? First of all, we can calculate the rate. So what's the overall rate of this encoding? Well, in the first round, we had a rate of we had 24 information bytes to 28 total that were written. All right. And then the second round, we had the 28 columns. Made the math easy. And we end up with 28 rows, and we end up with 32 rows. So if you just compare the amount of blue to green, blue to total, right, it's going to be exactly 3/4. So the rate of this is 3/4. In other words, 1/4 of what's finally written to disk is redundancy. All right. But what we really want to care about now is what is this going to do in terms of error correction? And there's a reason for the interleaving. This works very well against bursty errors. So, actually, let me do this. Let me say this. We'd like to look at the probability of error. But it turns out you need You need a correct noise model to really understand the probability of error here and why this performs well. Okay, so this is good for bursty noise. And it's not as good for scattered noise. Although it would still work all right. So, but its real strength is in bursty noise. What we mean by bursty noise is, suppose you have a sequence of errors in a row. You don't know where it happens, but when you get an error, you get a lot in that neighborhood. All right? Then what that means is, remember, we wrote this thing out to disk column by column. So let's assume there's a big row of errors. And I'm going to just draw a line through where the errors occur. So we have we have a big row of these things. First of all, the fact that the Reed-Solomon code works on bytes rather than bits already means that if you have a bunch of errors in one byte, it only counts as one total error. So you're already kind of anticipating strings of errors in a row. It would be bad if just one bit in your byte is in error, causes the whole byte to be considered an error, right? But notice what can happen here. First of all, if it's a small error, then the first layer will just correct it. That's fine. But let's look at the bad case where you have a big error that really pushes the limits of the Reed-Solomon code. All right. Well, what's going to happen is, say that error. How many errors could the first layer correct? How many byte errors? Let's say for one. Don't think of this whole chunk. Just think of a single column. How many byte errors can be corrected here? 2. Only 2, right? Because we have only 4 bytes of redundancy, and the errors count as double. So you can only do 2 errors. So that may not look like very much, but that's okay if you don't expect very many errors. If you get less than 2 in a single column that are an error, then it corrects no problem. All right? But if you get more than that, what's going to happen is the encoder at the first layer is going to declare an erasure. In other words, it's going to declare failure, right? It's not going to incorrectly decode. It's going to say, this is a bad column. And it tells that to the second layer decoder, right? So what that means is we declare everything in here, this entire, not just there, but we declare the entire row, declare erasure for the entire column. Okay, so that's going to help the second layer decoder, because as long as the first layer doesn't, how many columns can fail, and we still correct overall? 4 columns, right? Because each row can handle 4 erasures. We're assuming there will be no errors because all the errors would have been handled, either corrected or declared as erasures in the bottom layer, right? Or bottom or top. I don't know which one's bottom and top. So as long as we don't have more than 4 columns fail, then overall it completely recovers. All right, so that's the reason why it's designed this way. Okay. Any questions about that? Because we're going to move on here. All right. Oh, one fun thing to notice is, if you really wanted to break the Reed-Solomon code, by placing well-placed errors, and you got to go place them, how many would you need to place? Single bit errors. How many would you need to place to make the whole thing fail? 5. And how would you do 5? 1. No. Okay, so I think you need more than 5. 15. Okay, how would you do 15? Uh-huh. Good. So you you would take, from any 5 columns, you would make 3 symbol errors. And to make a symbol error, you only have to go change 1 bit in that byte, right? So you'd pick 5 columns, and in each of those columns, you'd go change 3 bits that are in different bytes, all right? You cause the column to fail its decoding, and now you have 5 columns failing, so it all fails. So 15 bits. There are more than 7,000 bits encoded here. And you only need 15 errors to actually make it fail. So that kind of illustrates, of course you had to go carefully placing the errors, but it illustrates that this is really strong against the block errors. Because if you have a long sequence of errors, you can have 3 entire columns wiped out. And let's say you have this long scratch that wipes out 3 entire columns and part of a fourth. Or actually, you could do all of a fourth and then even 1 byte of the surrounding columns, right? So this long string of errors, because each column here is 32 bytes long. You can do at least 4 of these columns and still recover, right? So there's a big contrast between how many errors can be handled depending on how they appear. Okay, how about error detection? So let's look at some, in the following part of the lecture, we're going to focus on finding, either detecting or correcting single errors, because there's some very nice simple schemes to do that. It'll help us understand this magic of how do you put redundancy and in a way that's going to allow you to correct throughout all the information. I should mention something I meant to write up here was that the Reed-Solomon codes. Two interesting things here. When they encode, so it actually uses finite field arithmetic here. So if you find Galois fields and algebra interesting, then this is a nice application of it, error correcting codes. And also, if you also the decoder for these things can be understood with the Fourier transform. I expect a big gasp. Okay, so that's pretty cool. I won't say how to do it. What? Yeah, over a finite field. Yep. Okay, so let's look at some simple error detection. All right. Okay, so we can do single bit error detection using a parity bit. So a parity bit works like the following. Let's say we want to put, we have 7 bits of information, and we want to make the last bit in our byte a redundant parity check bit. So we have something like this, 0, 0, 1, 0, 1, 1, 1. Here's our information. And the parity check works like the following. You set the parity bit so that the number of ones is even. All right. There's another way to state this. You set it so that the sum is even, or the sum mod 2 is 0. All right. So the remainder after dividing by 2 is 0. So in this case, that just means make it a 0. Okay, the parity bit. So okay, now any single error will cause your parity check not to work anymore, right? So you just check by, the parity check is take the sum of the bits. Take the sum, 1 to 8, bi mod 2, and you say, does that equal 0? And it should, unless there's an error. Now, what if there were 2 errors? Would you detect 2 errors? No, you absolutely would not, because 2 errors would bring the parity back in order, right? So this cannot detect 2 errors. What if there are 3 errors? Yeah. So it can detect odd numbers of errors. So, in fact, we care mostly about the 1 error more than the 3 errors and the 5. I mean, if you expect errors to be infrequent, then 1 error is going to be way more common than 3 errors. Okay, so it's the 2 and the 4 that we care about. So the problem cases would be 2 errors. That's the most significant problem case, right? Okay, so this detects and has some guarantees. It'll detect as long as there's no more than 1 error. So let's talk about actually being able to correct, to go beyond this and not only know that there's an error, but correct. And notice that the error can occur everywhere here. So this is a symmetric scheme. I mean, it protects equally all the bits. Okay, so what about correcting 1 error? And this repetition is the simplest way to understand this. So suppose that let's define a repetition code with some parameters. So the repetition code has 2 parameters. Let's say like a 3-1 repetition code means, and the 1, actually all repetition codes will have 1 as their second parameter. It means repeat each bit 3 times. Okay, so, and then you just decode the majority. So for example, the repetition 3-1 code, you're going to have your information would be something like this. If your information was a 0 bit, then you're going to, then the code word for this, which is what you would transmit or what you would write to the disk, is going to be 0, 0, 0. All right. If it was a 1, you're going to put 1, 1, 1. Pretty straightforward. And now, if there's only 1 error, you're still going to have a majority of the correct number, right? So this will also correct single errors. You could also go to more repetition, right? So you could look at repetition 5. And then you would have this. 0, 1 would go to 0, 0, 0, 0, 0. And now how many errors can be corrected? Up to 2 errors, right? Now, so this gives you a flavor of the fact that we can correct errors. When I was first learning about this, detecting errors, that made some sense, but it was pretty magical that you could actually locate and correct the errors. But when you look at the repetition code, you're like, okay, that's pretty straightforward. Go ahead. Yeah.
So is it 1 when you're correcting for 1 bit each time?
It actually, in general, you can write other codes besides repetition codes with these two numbers, mean how many information bits and how many total bits were written. It's just like the 1 here and the 5 there. But repetition, you're always just taking 1 and repeating it. So the way you use this code, of course, you have a sequence of real information bits you want. For each one, just like we Huffman coded, for each one, you go replace it with its repetition. So if you were encoding you wanted to encode 4 information bits, 1101, with the 3-1 code, it would be 111, 111, 000, 111. Right? Okay. Yeah. Did you have a question? No, okay. Now these codes are not that wonderful because if you really want a lot of error correction, you're getting to very low rates. Here, the rate, of course, would be the amount of information divided by the total. So this would be 1/5 rate of transmitting information. And so there are more interesting codes. One such family of codes is the Hamming codes. By the way, if any of you have used RAID on hard disks in a computer, that's usually they're using codes like these. Like, for example, the parity check is common to be used. But it's not just on bits, it's over the whole disks. You know. Okay, so the Hamming codes, this is a family of codes that correct one error. So you can make them longer and longer, these codes, and they have a certain amount of redundancy that they will always use. So, in fact, the repetition 3-1 code is a Hamming code. It's the first Hamming code. All right. The 5-1 is not a Hamming code, but the 3-1 is. All right. And let's look at the next smallest Hamming code. And this one is it's a 7-4. Okay, so this means you're going to write 4 bits of information, and you're going to end up with code words of length 7. Okay, now the fun thing about the 7-4 Hamming code is rather than writing its mathematical description, you can actually describe this with a picture very easily. All right, so let's draw 3 circles here. All right. And I'm going to label, there are 7 locations within these 3 circles. So let's call this one, let me get them in the right order, D1, D2, D3, and D4, P1, P2, and P3. So the idea is this: you start with 4 bits of information. Okay, they're in these spots here, and I'm going to label these bits D1, D2, D3, D4. All right, and then we're going to write onto this 3 bits of redundancy, right? And I'll label these P1, P2, and P3. And the way we do the encoding is you take the 4 bits you're given, let's say 0, 0, 1, 1. You write them into the spots in these circles. And then you fill in the other 3 spots so that the parity within each circle is even. Okay, so you have each circle represents a parity check. So notice each circle has 4 things in it. And you want them all to be even. So what that means is I go fill this out. What does P1 have to be? It has to be a 1 because you need there to be an even number of 1s in that circle. Right? And P2 has to be a 0, and P3 has to be a 0. So what you would actually write is this type of thing. So you've gone from 4 information bits, arbitrary, to 7, and you calculated those last 3 using this picture, right? Okay. Now, do you see how we can correct any 1-bit error, no matter where it is? Okay. So someone thinks they see how, so I want to volunteer to do this. Yeah. So I want to volunteer. You want to volunteer? Okay. So what we're going to do is we're going to, well, let me demonstrate once, and then we'll let you volunteer. So in this case, if there was an error, say here, D2, and that what became a 1, the question is, could I look at this knowing there's no more than 1 error, and could I tell where the error is? And I can, and so we'll demonstrate it by doing the following. If I could get you to leave the room. Okay. So I need one person. These jobs are easy now. I need you to, oh shoot, are all people? I need someone to come write in 4 bits, just whatever they want. There's not. This part's easy. The next part's only slightly harder. Volunteer? Okay, come on up. So write the first 4, the D1 through D4, and then write them both here and then in the picture. Yeah, whatever you want. Okay. Great. Thank you. Okay. Now, someone come calculate the parodies and fill those in. Okay, come on up. Excellent. Yeah, and put them there so we can see how you did it. Excellent. So you made it even in each one of them. Perfect. Okay. Now I want one person to pick a number between 1 and 7, and that will be where we place an error. But you have to be very quiet. Don't let her hear. So who wants to pick? This is maybe the easiest part. Yes. Okay. So I hope she can't read my handwriting. Okay. Oh no. Okay. So there we are, right? So she's going to come in and tell us what the information was. Okay. We're ready for you. Okay, so what we want to know is what D1 through D4 is after you correct. So can you correct this and then tell us what the information is? Yeah, they match. What was that? We are. Or 0. Okay, perfect. Good. So you noticed that P2 was the error. That should be a 1. That should be a 1. And the information then is just exactly what was not affected. And we would just pull it out. Okay. Good job. So you check it by checking the 3 parodies. And you see if they all come out okay, then there were no errors, right? If they all, but if there's, you look for the intersection of where the parody mistakes are. In this case, this was the only one where the parody didn't check out. So it had to be only this place here, right? But if the parity didn't check out for P1 and P2, had to be the one spot that could have affected both of those with a single error. An error in D4 affects all three, right? So forth. So that's how we correct. All right. So pretty cool. Now, to generalize Hamming codes, because you can make them bigger and bigger, and you don't have nice diagrams like this for all of them. But what they all are, you can actually generalize it. If I rewrote the order of the P1s, so if I rewrote things in this order, seems like a weird order, but then I can show you that I can write the parity checks in a grid here. I can show you that the parity checks are the following. Every other one gets checked. And then you have this pattern. On to, off to, on to, off to, and then you have this one. So this is the same thing. So the x's, if you have a bunch of x's in a row, then it means check that as a parity check. Okay, add those up. And you could then go to the next Hamming code. You put another parity here. And then you put a bunch of data. And then the and you continue the pattern. So you check there, check there. Whoops, don't check. Whoops. No. Check there, there, so forth. Okay. And you're going to have another column, another row here for this guy, and it's going to be like this. And in fact, if you haven't seen the pattern, you'll notice that we're just, if these are ones and zeros each column, this is just counting in binary. Okay, so there's a 1, 2, 3, 4, where the least significant bit is the top. All right. So if you just use that pattern, every time you get to a carry, you do another parity bit. And this will get you all Hamming codes, actually. But you have to stop at powers of 2 minus 1. So you have a Hamming code of length 7, Hamming code of length 15, and so forth. And they will always correct one error, up to one error. And as you've noticed, we could have, it was mentioned here, we're assuming when we decoded that there's only one error. We could have, if there were 2 errors, what would happen? Could we detect it? At least throw our arms up and declare failure? Mm-hmm. Yeah. Were you going to say something? Yeah, you would actually decode it incorrectly to another one. Because the Hamming codes are one of the very few codes that are sometimes called perfect codes. Now, perfect code sounds really great, but it means one specific thing. It doesn't actually mean that we're going to want to use this code all the time. Perfect code means that it covers the space. So what that means is any code that can correct up to a certain fixed amount of errors, you can, if you abstractly draw the space of all possible 7-bit sequences. This is some crazy space, 7-dimensional, but it binary in each dimension. And so all I can do is draw a cartoon picture of it. All right, and I could say, well, we have this space of 7-bit sequences. All right, that's just this thing here. Okay, it's a big space. And we could then say, well, you have only some of these sequences are valid Hamming code words. In other words, 7-bit sequences that you would say have no errors. That you could have gotten by doing Hamming encoding. So those are the code words, right? You have some code words. And to guarantee that you can correct up to 1-bit error, it means that there's some spacing between these code words. If you draw what's called the Hamming ball, In other words, take every sequence that only takes one bit flip from the code word. Okay? These are everything that could occur from one error. They should not overlap. So Hamming ball of radius 1 So because it corrects one error, we'd look at Hamming ball of radius 1, and it's centered on each code word, and there should be no overlap if it's a single error correcting code. However, there can be gaps in general. For the Hamming code, there are no gaps either. Okay, there is very rare. You don't get codes that have that have this separation and also no gaps, but Hamming codes do. All right, and that's why they're called perfect codes. So there's no space, no code words in the gaps. So in this picture, I have gaps, but in the Hamming code, there's no gaps. All right. What that means is if you have too many errors, it's going to correctly decode. It's going to decode to the wrong thing. All right. You're never going to see if there were gaps. Then at least the decoder could say, well, you don't really fall in any of my good spots, so I'm going to say that it was a failure. But that doesn't happen with the Hamming codes. There's certain you can take advantage of this and do some interesting things with them, but we won't have time to do. Okay. So I want to show you how we can analyze the probability of error of these things. All right. So and the reason I say that is we really aren't interested in saying that you can just decode up to exactly one error. We're interested in saying, if I write this to some memory, or if I transmit it over some wire or something, and if each bit has a certain known small probability of flipping, okay, this is called the binary symmetric channel. We call noise a channel sometimes, and we say the binary symmetric channel says there's a fixed known probability with which each bit might flip, okay, and under that model, what's the probability of error? There's some chance you get more than one bit flipped in a block, right? So we can calculate that. So under the binary symmetric channel model, then we can say, okay, let's compare a couple of things here. So we'll suppose that each bit flips with a certain error. And they're all independent. So we have some PB. That's the parameter that says the chance of each bit flipping. All right. So for repetition, let's look at repetition 3.1. Okay. The probability of error in this block is that we have to have either 2 errors out of the 3 bits or 3 errors, right? If we have only 1 error, it gets corrected. So we can calculate this probability by just adding up all the events that lead to error. How many ways can you have 1 error in a block of 3? There's 3 different ways. Could have been the first one, second, or third. So we have to multiply by 3 times the probability of any one of those sequences. I'll say 2 errors. Actually, yeah, I'll write 2 errors here, but I might confuse some people. Plus p, the probability of 3 errors. Maybe I should do this. I won't put the 3 there. And I say we either get 2 errors or 3. But in the next line, I'll say 2 errors. There were 3 ways to do it. And each one of those ways had probability PB squared times 1 minus PB. So this we get from saying, take for example, the chance that you had error, error, no error. That particular sequence of events, right? That chance is going to be the chance of error was PB times the chance of error again, PB, times the chance of no error, which is 1 minus PB. Okay? Because they're independent, you multiply. Right? Now, then we would look at another error sequence, like error, no error, error, and we'd multiply and we'd see we get the same number. So that's where the 3 comes from. The 3 different ways of getting 2 errors. Plus, and then there's only one way to get 3 errors, and there we get PB squared, so cubed. Okay, so there's the probability of error over a block for the repetition code. Now for the Hamming, we'd do something similar. And we would say, this is the Hamming 7.4. We get an error if there is more than 2 or more bit errors. Now here, it's going to be easier because there's so many ways you could get 2-bit errors, 3, 4, 5. We'd be adding up a bunch of stuff. So we could also calculate this by saying that's 1 minus the probability of not getting a block error. In other words, 1 minus the probability that we get 1 or fewer bit errors. This will be a little bit easier to enumerate. All right? Probability of 0 errors minus the probability of 1 error, 1 bit error in the block. So that equals 1 minus, the probability of no errors would be 1 minus PB to the 7th. And then the probability of there being 1 error, there are 7 ways to get 1 error, and each one has probably PB times 1 minus PB to the 6th. So you can calculate this exactly, no problem. If you want to get a sense of how big this is, when PB is small, this is roughly 21 PB squared. So if you want a ballpark figure, and this is helpful because you want to know, well, you want to get some intuition for with the difference between the repetition and the Hamming. We see that when they'll both be dominated by this the square term in PB. Because if PB is very small, the cube term won't be very important. So I made this approximation by dropping off all of the higher order PBs. Okay, so this is going to be roughly 3 PB squared. Those will all be close to 1 if PB is small. And this will be like 21 PB squared. So it's actually like, it's worse, 7 times the probability of error. They'll both be small, but it'll be 7 times as bad. Now, if we didn't do any encoding, then the probability of an error is just PB itself. Okay, so it's much better when PB is small. It's much better to go from PB chance of bit error to PB squared. We'd much rather take that exchange. But we see that this repetition code is doing better at protecting the error on the blocks than this for small PB. Why is that? They both protect up to 1 error. Because what? I heard mumbles. Exactly. You're more likely to get 1 out of 7 than 1 out of 3. Okay. So you actually then have you can make an interesting graph here. You can say, for example, let's take PB equals 0.01. Okay. I have a table here now. If PB is 0.01, then we have here's the probability of error over the block, and here's the different codes. So we have Hamming, and uncoded. Uncoded means just transmit your bits. It's got parameters 1, 1. Okay. For this particular bit error probability, the block has error with probably like this, and the and unencoded is like this. Okay, so much more error for uncoded than for the others. And if PB was smaller, we'd see a bigger separation here. Now we can make a plot that would be of interest that would say, here is the rate of the code, and here is the probability of error. Okay, so we have the probability of errors here, and the rates are easy to get, right? The rate is 4/7 for this Hamming code. It's 1/3 for the repetition code, and it's 1 for the unencoded. So we get some points here. We say, well, you're not going to get a rate more than 1. 1 means unencoded. And so that is going to be something like this. So this, I guess, is 0.1. And then we have the repetition code is down here. Sorry, repetition is all the way down here to 1/3. But the error probability is much less. It's only 2% of that first one. So it's way down like this. Okay, and then we have a Hamming code, and that is a 4/7 rate. All right, and we have the error probability something like this. Okay, so there's a graph. Now, the directions we like here, we would like to keep the rate high. That's this way, and we'd like the error probability to be low. So a good code wants to go down and to the right here. We would like to good performance means down and to the right in this graph. Now, what's interesting is you might say, let's keep this noise model. We have a particular noise model, right? It's binary symmetric channel with crossover 0.01. Okay. And we can ask, we only looked at 3 possible encodings. There are infinitely many ways to encode. And we can imagine that there's some region of performance that's possible with error-correcting codes. I will use yellow here and fill it in. We know for sure we can get these performances, so I'm going to connect them because we also know the region of performance is convex. Okay. So as it is, and we know that with longer and longer repetitions, we could make this rate go really low, but the probability of error would go low too. So we know it kind of connects at least like that. Okay. And the question then would be, what is this lower frontier of possible choices of good error-correcting codes? Is this making sense? This is a fundamental question that needed to be asked and answered, and it was answered. At least a very important insight was answered by Claude Shannon, and so that this is really the breakthrough of information theory, is to say, not only so the picture I've drawn here might have qualitatively looked like what people thought was the case before information theory. That if you want to get good reliability, you have to take your rate very small, okay, and you have some fundamental trade-off there, and that's not actually true. So if you search over the space of all possible error-correcting codes, you actually get that there are codes that perform, let me get this correctly here, there are codes that will get you, in this case, all the way to this vicinity here. So I'll put a bunch of dots here, that none of the ones we looked at, but there exist codes way down in some corner here, meaning that the best codes fill up this type of a picture, something like this, and they meet the x-axis at a point that we can calculate. Okay, so what this means is there are codes. It's actually hard to figure out and to design these codes, but you can prove that they exist, and a lot of technology over the past decades has been trying to design codes that will get you this kind of performance. But we know that the best codes will get you arbitrarily small error at rates up to a certain calculatable point called the capacity of the channel. Okay, for this particular channel, we know I can give you what that number is for this particular amount of noise. C equals 0.919 bits. So that's the rate of the best codes for this particular noise. And in general, we have a formula. You give me any noise model, any memoryless noise, assume that each symbol is affected independently. But it doesn't have to be binary symmetric. It doesn't have to be, it doesn't even have to be binary noise. Okay, and there's a formula for calculating the capacity, and believe it or not, that formula is it's a function of entropy. So here we get that entropy shows up again in a fundamental limit. And so it's really a pretty fundamental quantity. For this particular case, for binary symmetric noise, the capacity for, I'll say, binary symmetric channel, as we've been discussing here, the capacity as a function of PB is exactly this. It's 1 minus the entropy of a binary variable that would have that probability. So you might recognize what I'm subtracting here is this entropy function we've been looking at. So that's the answer for capacity for this particular set of channels. If you were to graph it, it's just 1 minus the binary entropy function, which we've already looked at. So this is C, and this is PB, and it's just like this. And it's when the error probability is a half is the worst possible case. That means what's coming out is complete garbage. And there's no way to communicate, no way to store anything useful in that setting. But if the error is more than a half or less than a half, you have symmetry. You don't care whether, if bits are more likely to be flipped or not, it makes no difference as long as you know which situation you're in. You can just flip the output, right? So you have a symmetry for the capacity. Okay, we'll do secrecy next time. And then we'll get back to Fourier transforms as well.